Hi everyone, my name is Dami. I'm a second year engineering student at Jesus College, Oxford, and I'll be doing this lecture today on operational amplifiers. Um, so let's get started. Right, so operational amplifiers is actually something that we covered in first and second year, so I thought would be a good introduction to what studying engineering is like. Um, this presentation slash lecture was inspired by the engineering science course, and here is a brief structure of what we're going to be going through today. So I started with a brief introductions to what op-amps are. So we start with discussing what are op-amps, and then we go into the difference between ideal and non-ideal op-amps. I then hope to briefly summarize the different types before going into a bit more detail about some of them. I was really hoping to go into detail about all of them, all of the ones I've covered, but there isn't enough time. So um, I won't be able to do that today, but we will get through a lot of them. And I've also added some like further reading if anyone would like to do that. And then I hope to end this lecture by talking about mitigating climate change, because I've heard that you have to do a project about that during this summer school, so that should be good. Right, what are operational amplifiers? It kind of comes from the word operational and amplifiers. It sounds silly, but it literally is what it sounds like. So operational, that means it can perform operations such as addition, subtraction, filtering. It can also do differentiation and other things like DC to analog conversion, digital to analog conversion, sorry. Um, and then the other part of this amplifiers just basically means what it says. It can amplify input voltages to much bigger output voltages. So we're talking about, for example, going from 10 millivolts to like 5 volts. We'll go into detail about why this is super important later. But yeah, this is what operational amplifiers are. They are devices that amplify the difference between the input voltages into bigger voltages. They can do other cool things as well, which I hope to discuss later. But this is the basic of it. They often use feedback, and feedback is just that loop that you can see there, like going back feedback, alongside components such as capacitors and resistors to perform operations, as I said earlier. So yeah, they're really cool things, and you find them in many analog circuits. Right, ideal versus non-ideal op amps. So non-ideal, it's also, I might also refer to it as real op amps, because I think kind of like at school you hear about like real resistors and ideal resistors. You have a similar thing with op amps. You have the ideal one, which makes calculations easier, and that's like the best case scenario, and we actually have what happens in reality. So the images on the presentation right now shows the configuration of an ideal op amp and a non-ideal one. What I would say is an ideal op amp is basically a special case of a real op amp. You basically just impose certain constraints on it and you can get an ideal one. In reality, kind of linked to the name, we can't get an ideal op amp, so we in reality we do tend to work with real op amps. In the next few minutes, well, I said few, but like the next 40 minutes or so, we're going to talk about ideal op amps. We'll focus on ideal op amps. Um, this means that on the left diagram, we can conclude certain things. So the first thing that we can kind of assume is that we've got infinite input impedance. Um, what this basically means is that Ri in the diagram you can see above is equals to infinity, which is great because if you look at that loop there, if Ri is equals to infinity, that means the current at the plus sign must be zero, and the current at the negative sign must also be zero, because there is like infinite resistance through that loop, which is another assumption that we use in the calculations in the next few slides. Another thing that we can assume for an ideal op amp is that you've got zero output impedance. So RO there is equal to zero. And another super important one, last but not the least, is that we've got infinite differential gain. So that means A in the diagram there on the right has a gain of infinity. We'll see why this is useful soon. I don't want to go into that much detail, but basically what this means um, is that we can make certain simplifications. Um, And then the final one is that when connected in feedback, as we use in most cases, we can also assume that V minus is equals to V plus. So when I'm saying plus or minus, I really don't want to confuse it. It's just the plus and minuses on the diagram. So if you can maybe put a dot, if you imagine looking at that point, V plus will be equals to the V minus there as well. So those are the main notations that we're going to use in this lecture. I'm just going to go through it again because it's really important that we understand it. So if you can just focus on the diagram on the left, which is the ideal one, we tend to have a non-inverting input, which is the plus one. And then we have an inverting input, which is a minus one, as you can see there. You tend to have a positive power supply and a negative power supply, and then you also have your output voltage. For an ideal op amp, I'm just going to repeat the assumptions again. We assume that our input current is equals to our output current are equals to 0. So I minus is equals to I plus is equals to 0. That's the first important assumption. Our second important assumption is that V minus is equals to V plus. And that's something that we can assume when we have this feedback connection, which we are going to have for the entire lecture. I think those are the main assumptions that you really need to know right now, and those are the most important things. Yeah, so we're just going to move on to the next slide. Right, next I would like to talk about the different types of op-amps. So we've kind of discussed what op-amps are. They are things that you can use to amplify input signals. You can also use them to do certain operations. When I refer to certain operations, you might be thinking what type of operations. I kind of mentioned them in the first slide, but this list kind of gives you an insight into what these kind of operations are. So we've got something called a voltage follower, which I'll talk about in the next slide. We've also got a non-inverting amplifier, which we'll also see soon. It just increases the output voltage and doesn't invert it, which that goes by the definition, the name. We also talk about something called the inverting amplifier and then the summing amplifier. And then the last two, we don't really have time to go through those, but those are the differential amplifier and the instrumentation amplifier. They follow the same steps, and we covered those very in depth in the first 2 years of our engineering science course. So those are really, really useful ones as well, and you use them for many things. There are a lot more different types of op-amps. I don't have time to name all of them here, but the idea is that there are many things that you can do with an op-amps, and they're super useful in the electronic world. Right, okay, so the first example that I said we're going to mention was the voltage follower. So this is a type of op-amp. It's the simplest type of op-amp, I would say. As you can see, there's no resistors, there's no capacitors or anything there. It's just a simple loop. So we want to figure out the relationship between the output voltage here and the input voltage. So you might be thinking, how do we do that? Well, if you remember the constraints for ideal op-amps that I mentioned a few slides earlier, and I said it was super important, we're going to have to use those here. So the first thing that we can notice just by looking at that circuit there, just simply looking at it, we can see that the V plus voltage is equal to the V in voltage. Just looking at that bottom line there, that's fairly straightforward. The second thing that we can notice is that the V minus, that voltage V minus, is also equal to V out. Also, you can see that simply by just following that line. So we need one more constraint, and that's what we get from an ideal op-amp. From an ideal op-amp a few slides earlier, I told you that you can assume that V plus is equal to V minus. This is super useful because we can then combine these three equations to figure out that V out is equals to V in, which is great. This tells you that your gain by definition is just your ratio of V out to V in, so your output voltage over your input voltage. Since we figured out that V out is equals to V in, we can tell that our gain is equals to 1. So for a voltage follower that we've got here, we've got a gain of 1, and we've got that our output voltage is equal to our input voltage. Right, this is great. We've done our first calculation. We found our first expression. You might be thinking, this seems a bit extra to find out V out is equal to V in. Like, why do we need this? Yeah, it's very useful for several reasons. As I said earlier, ideal op-amps have infinite input resistance. And then we then said this infinite input resistance means that it has zero input current, so I minus is equal to zero. What this means is that it draws very little power from the input circuit. Um, and this is really good because it avoids the source being unable to supply the desired power. So it avoids this phenomenon called loading. And loading just means that where you have an input circuit being unable to supply the desired power. So I'll just repeat that again. The reason why we need this is because ideal amp amps have infinite input resistance, which means that there's zero current being drawn into its input there, and which means very little power is used there, which is really good because it avoids loading. Um, I know I said at the beginning that in reality we don't use ideal op amps do not exist. You always have some realness to it. But even with real op amps, the resistance are really high, and it means that once again very little power is drawn from the input circuit, which is really good. Um, why is this useful? This is super useful because it makes for a good buffer. A buffer is a device that provides a voltage equal to the input voltage but without altering the original circuit. It's used for several things, and I think it's even used in the either the differential instrumentation amplifier. Um, but yeah, it's really good because we can then use it as a buffer, and we can also avoid this phenomenon called loading. Right. Our second example that we're going to mention today is a non-inverting amplifier. So I've showed the circuit there. If you can just take a moment to look at it. I've also shown the result that we're aiming to get. I'm just going to switch to my note-taking app because I feel like this is a good thing to show by writing rather than just saying it out. So I'm just going to switch to that app, and so I should be able to share my screen now. Right, if this was a live recording, this would be the point where I'd ask if anyone has any questions. But please, if you do have questions, please get in touch with the Syrian Summer School team, and I'm really happy to explain anything. So what we've got here is our I believe you should be able to say that non-inverting, slightly slow, non-inverting amplifier. Sorry, my handwriting's a bit funky. Right, so what do we have here? We want to figure out the relationship between V in and V out. How do we do this? So first thing that we can notice, if we look just up here, we can say V in is equals to V plus, just by looking at that place there. What's the next thing that we can do? We want to look at the other side, this section here. We can kind of draw a simplified diagram actually to help with that. So we've got V out. You've got a line that's going to, sorry, my laptop is just being slightly slow, but you should be able to see it. You've got this line here and you've got it connected to ground. You've got that node here, and you've got V out here. So this is me just drawing this loop here, make that clear. This loop is over there. So just going to rub that out to avoid any confusion. Right, so we've got something that looks like this. This is R2, this is R1. We want to find out the relationship between, V in and V out, just to remind us of what we're doing. If we look at this node here and just trace it back to here, we can see that this point here is V minus. At school, you should have covered something called a potential divider. If you haven't, please, I do suggest that you look that up. It's super important that we use it in several electronics applications. It's like one of those things that are actually useful in school. They never really go away. So if we use the equation for potential dividers, we can see here that V minus should be equal to, if we look very carefully, R1 over R1 plus R2 times by V out, which is all good. So what can we use next? So we know from our ideal op-amp expressions, once again, we're going to use those just as we've done with the voltage follower. So sorry, the handwriting's gone a bit wobbly. We know that V minus is equals to V plus. Why is this useful? Let's just label this equation 1. Let's label this one 2. And let's label this one 3. If we, what can we do? If we sub 3 into 1, so we're putting 3 into 1, we get that V in is equals to V minus, right? So just by using 3 and 1. And then let's just label this 4, equation 4. I'm just gonna move this other diagram to the bottom. We label this equation 4, this here. We can then substitute equation 4 to equation 2. Put 4 into 2. And we get that V in is equals to R1 plus R1 plus R2 times by V out. And so we can say that V out is equals to R1 plus R2 over R1 times by V out, which is equals to 1 plus R2 over R1 times by V out. Right, I hope those steps were clear. So we just start by looking at following the voltage. You can use different approaches. You can use Kirchhoff's voltage law, which is kind of what we've done here. Following the voltage across the loops, this is for the top loop, this is for the bottom here. We get two expressions. We then use the ideal op-amp equation that we know, V minus equals to V plus. We rearrange and substitute, combine those together, and we get this expression. This should say V in. Sorry, I think that would have been the point where someone corrected me in a live lecture, but yeah, that should say V in. And we get this expression here, and if we just go back to the lecture slide, that should be what we've got. Yes, so we've got 1 plus R2 plus R1 times by V in. Oh, sorry, I just realized that when I rearrange, I didn't change my subscript. Just make that clear so I don't confuse anyone. So we've got V out here, so this should be, because we're rearranging for V out there. This should be V out, and this should be V in, and this should be V in. Sorry, my starter just let me slow. Right, so I hope that was clear. I'm going to send this notes as well so you can look through that just to understand it better. Just going to go back to share my screen. So that was for a non-inverting amplifier. And so that tells you what the relationship is between V out and V in, and you can use that to find the gain. Once again, the gain is V out over V in, and so that's going to be equal to 1 plus R2 over R1. R2 and R1 are just resistances. So why is this type of amplifier useful? It's useful because you can use it to achieve high gains, and it also avoids loading that we've talked about. Right, so the next example that we're just going to quickly go through is the inverting amplifier. And the expression that we're looking to get is V out is equal to minus R2 over R1 times V in. The negative there gives the hint about the inverting phrase there. But we're just going to quickly show that in the good notes as well. I'm just going to skip here and show that quickly. I just think it's so much useful to do it on the screen than for me to talk through it. Um, sorry about the slightly delayed transition. That should be done. Right, so we're looking at the inverting case now. So same thing as we've done before, we start again. If we look at this bottom here, we can see that V plus is connected to the ground. So that tells us V plus is equal to 0, since it's connected to the ground, right? Oh, that's not 0. I think my stylus is having a mind of its own. So yeah, 0. So if you look at the top now, once again, we can kind of redraw this as a potential divider. So we've got actually, how about we take a different approach? So we're using different circuit approaches. So we're using different techniques. How about we look at the current going through? Let me just change the color. If we look at the current going through this loop here, sorry, slightly slow. If we look at the current going that loop, we can actually write an expression that says V in over R1. Sorry, that should say R1. R1. I will edit this. The handwriting is slightly messy. Is equals to plus, because we're summing the current into that node there, plus V out over R2 over R2 is equals to the current through there, because you're adding up to make I minus, and we know that I minus for an op amp is equals to 0. So let's just write that I minus, which is equals to 0. Sorry, it's really coming up slowly. That should say is equals to 0. Right, and this is here is because it's an ideal op amp. I will write that in the notes later to save time and move on from there. Yeah, so we get this is equal to 0. If we then rearrange this expression, we can get V out V out is equals to, we're going to have minus R2 just by rearranging the top there over R1. So sorry, this is rather slow. That looks very messy. As I said earlier, I will make sure this is tidy before it gets to you. I'm so sorry. I don't know why it's turned to O. I'm just gonna edit that. Over R2. Yeah, R2 over R1 times by the in. Right, cool. Which I believe is what we're trying to find. So I'm going to talk through the steps again. We go through the loops, and then we then use the fact that an ideal op amp has I1, I minus is equal to 0. I will make that clearer in the notes before I send them over. But let's just compare that to what we have on the spread on the slides. Yeah, and which is what we expect. So our V out should be equal to R2 over R1 as expected. Right, why is inverting amplifier useful? It's useful because you can use it in many audio applications such as low impedance microphones, because I think it generally tends to have an overall low impedance. It's called an inverting amplifier because of the negative gain. So the minus one there shows that it's been inverted. So V in is a negative sign. It's like the negative, it has a negative sign compared to V out, the output voltage. And so that's just a brief summary into an inverting amplifier. Right, and then the final one is a summing amplifier. A summing amplifier is one of the widely used ones as well as an inverting one. Summing amplifier is used in many applications. It normally includes multiple input voltages connected, and there's normally like a virtual earth summing point, as you can see there. N1 is a virtual earth summing point. Yeah, and then we just have a regular amplifier, as we've seen in the first two. Why do we need a summing amplifier? Well, a summing amplifier is used in many applications where you need to add two or more voltages. For example, if you have a digital to analog converter, or if you're mixing audio signals. So if you've got multiple audio signals that you want to mix together without changing any of those signals, without affecting the integrity of the different signals, you want to mix them, then a summing amplifier is a good way to do this. Note that once again, we've got a negative gain, which is quite similar to the inverting amplifier that we just derived earlier. I do want to derive how we got this, but my drawing pad wasn't really cooperating, but I'm going to try to do that again as quickly as I can. Once again, I'm just going to move on to my notes app and try to derive that carefully. Once again, it's a pretty straightforward one. And I forgot to mention earlier with all the examples we've covered, but you can approach them in different ways. And I think when approaching them in different ways, you find that you get the same answer at the end of the day. So you can either use the potential divider methods that we've used in the first example, or you can use, you can consider the current entering a node as we've done in the second one. With this last one, I think we're going to use the current going into a node approach. Just trying to settle down my thing. Cool. So here we're going to consider the current going into N1. So we're going to use Kirchhoff's current law. I believe we should have covered that at this point. But Kirchhoff's current law just says that all the current going into a node, just as we've used with this example, should add up to 0. So they should all add up together. So they should sum together. Basically, that's Kirchhoff's current law or charge law, either of those two. So we're looking at N1 here. What does this tell us? We know that I minus, so here, so I'm trying to do a circle about that. We know that the current there should be equal to 0 because that's the condition we have for ideal amplifiers. Just as we've said here, I minus should be equal to 0. So if we apply Kirchhoff's current law, we can write that I1 is equals to, sorry, not equals to, plus I2 plus I3 is equals to IF. Quite straightforward. And that's just by looking at that node here, N1, and knowing that the current going out this way is 0 because we've got an ideal op amp, and so I minus is 0. Just clarifying that in case I didn't make that clear earlier. Okay, cool. Now that we've got this expression, what can we do next? We know that current is equals to voltage over resistance. So we can say here that we've got V in 1 over R1 plus V in 2 over R, oh, sorry, that R has gone wonky, over R2, oh no, not again. I'm really sorry about this. This will be the last notes example. So I just wanted to be okay. I'll come to that plus B in 3 I think actually my stylus has been super delayed. I'm really sorry about this. I'm just gonna move to typing it with typing it on the screen instead. Right. So what we end up having there is V in 1 over R1 plus V in 2 over R2 plus V in 3 over R3 is equals to V out over RF. And this is just from the equation above. And so this is very nice, this is very simple. And we can then just rearrange it around and to get, oh, sorry, there's been a slight error change. This should be, it should have been a minus because of the direction of the currents. Just make this clear. Because I minus I2 and I1 are going this way. Try to rectify that, sorry. So this should be minus IF. And that's just by the direction of the current as drawn on the screen. So that'll be minus. Roll that up and make that clear. And so if we arrange this around, we've got V out is equals to minus RF minus RF over R1 V in V, that's multiplied by V in 1 plus RF over R2 multiplied by V in 2, and you get the gist. It continues like that. Right. Might just do the last one for completion. RF over R3 times by V in 3. Right. And that's what we get from the expression above. Let's go back to the slides. I do hope that was clear. Once again, if you've got any questions, please do let me know. I'll make those notes a lot more neater when my stylus is working better. I might handwrite it and get that sent across as well. And so we've got this expression that we've got here. As I said earlier, a few things to note. You've got a negative gain again, which is quite similar to the inverting amplifier. And as I said, it's used for many things. This and the inverting one are one of the biggest ones used generally in terms of op-amps. Right, so we've gone through the different types. We've gone through a regular voltage follower, which is a simple one, non-inverting, inverting, and a summing amplifier. As I said earlier, there's a lot more to cover. I don't think we've finished learning all of them. And I wish I could have gone through more of them today, but there is a lot more. And more has been covered in the first years of my engineering science course, which I've really enjoyed doing. Um, we've covered other things such as non-ideal amplifiers. If you remember, I said we're assuming certain things just to make the calculation simpler, but we can sometimes account for those non-idealness, and we're able to calculate with those as well. So we've covered that. We've also covered differential amplifiers, which you can see on the image there, so the left one. Once again, you can easily find out the gains just by doing the steps that I've shown you in the first few slides, in the slides, the last few slides. It's basically the same step. You follow the voltage around. Sometimes you look at the current nodes, and then you use the I minus is equals to I plus, and then V minus is equals to V plus expressions. And you should be able to rearrange. You can either rearrange step by step, or you can solve simultaneously if you want to. And also we've covered something called an instrumentation amplifier, which is on the right actually, to the other image. And you can see what I was referring to earlier about a voltage follower being used in other amplifiers. If you look at the left, I think the left, yes, you can break it down into two voltage followers that we covered at the beginning. I know there's a resistance there, but it's kind of a similar structure. Once again, you can solve this using the steps I've shown you in the last few slides. And I do encourage anyone who has some spare time and wants to do that, please do attempt them and see how far you get with them. Yeah, they're using many things and they're super useful. And it's kind of nice to get that experience of doing that and seeing how the voltages relate to each other. In terms of further reading, if anyone's interested beyond calculating the gains for these two examples, there are two reasons that were suggested during our course. One's called The Art of Electronics, and another one is called Design with Operational Amplifiers and Analog Integrated Circuits. So if anyone wants to do some reading on those, please do check those out. Yeah. And next slide. Right, so I've been told by Matt that one of your projects for this summer school is about mitigating climate change. And I wanted to add like a link to that at the end, just to bring it all together. So I hope through the examples, the writing on the board, although those were a bit funky, I hope I've been able to show that there are many, many applications of op amps in electronic circuits, and there are many things that you can do with them. You can add, you can subtract, you can sum, you can filter, differentiate. A lot that I haven't talked about, but there are many things that you can do with them in an electronic circuit. And you might be thinking, how might this link to mitigating climate change? Well, there are possibly plenty of routes that you can go with this, but I think the first thing that I thought about is in terms of robotics. So as I said earlier, operational amplifiers, a key point is that it can be used to amplify signals. So in robotics, sometimes you might use a microcontroller in your robot. Most times you're going to need a microcontroller in your robot. And sometimes you might have really small voltages, like 10 millivolts. And sometimes a microcontroller might not be able to measure that. It probably can't. And so you want to amplify those voltages. That way you can then work with those. And this is where an op amp might come in. The other uses of op amps, so as I said, the digital to analog converters that you can also apply in this scenario. But that was one of the examples that I came up with. So how is that then related to climate change? Well, if you think about it, robots can be used in many ways to mitigate climate change. And when I was trying to figure out some of the ways, I found this really useful article that I've also included a link at the bottom here. And I think it raised some key points. And one of the first things that it said, you can use robots to build and maintain renewable energy infrastructure, such as wind towers and solar farms or hydroelectric generators. You can use robots to help you do that. It reduces the workload. It makes things a lot more accurate. It makes things a lot more efficient. So you can use it there. And I think renewable energy and it has one of the biggest biggest and most important ways to mitigate climate change. We know that the amount of energy we're using from fossil fuels and non-renewable sources is causing so much harm to the environment. So finding a way to make renewable energy infrastructure more efficient, more more efficient, and to like be able to produce enough energy during all periods, peak periods and non-peak periods, is super important. So I think that's one way that we can use robots to mitigate that. Another way the article mentioned was to fast track the restoration of natural resources. What this means is that there are certain things that we've done to our environment and we've done to the earth that have caused so many damage, and there's certain steps that we can take to kind of restore that. It might not be immediate steps, but there's certain things that we can do. And one of the things people often mention is planting trees or yeah, and things like that. And I think robots can be used to once again make that process quicker. And that's something that you can possibly think about. And a final one, which is kind of the more obvious one, is using robots to collect data. If you think about the world today, data is super important. It makes it easier to understand the world. It makes it easier to get solutions to things. If you think about building, growing industries, you're thinking about artificial intelligence and machine learning, and industries like that need a lot of data um, to work. And so, one thing that engineering can be used for is to possibly design a robot that can collect data in even certain environments that humans may not be able to go to. We can design a robots to do that, and hopefully get a better idea about the effects of climate change and ways to mitigate that. Um, but yeah, so those are the three things. So helping to create like renewable energy infrastructure, helping to fast track restoration, and also being used to collect data to aid scientific research. Yeah, I hope this is useful and this gives you something to think about. And yeah, you can feel free to check out the website that I attached here. I'll also be providing the slides later, so you should be able to have that very easily. Right, I think we have come to the end of my presentation. I really enjoyed speaking about this, and it's been nice to share what we've done in the last 2 years with you. Um, Please get in touch with the team for slides and notes. I will be providing this, and also for corrections and questions. Questions, most importantly. I think it's really important to ask questions if there's anything that wasn't clear. Maybe I speak too quickly or too slowly at some point, or um, you just want me to go over something, please do get in touch with the team and I can provide like a written answer to that and get that sent to you. Another good thing is if you spot any corrections, any signs that I may have gotten wrong, or any numbers that I may have switched around, please do let me know. That often happens. So it'll be useful to have that so I can correct it for everyone, and so everyone benefits from that as well. In terms of the written notes that I attempted to do during the session, I will edit those and get those across as well. Um, Thank you for listening. I really hope this is useful, and I really, really hope you enjoy the rest of the summer school. Thank you.